a programmer, a geek, a hacker of signals. Oona is interested in radio, digital signal processing, sounds, visualizations, mysteries, music and sound art, and vintage technology. Please welcome our keynote speaker, Oona Räisänen.
Hi and welcome. We'll take a look at decoding analog video with an SDR. This talk is sort of a story. I'll tell you two related signal discovery stories from my own personal perspective. How I discovered a mysterious video signal and decoded it and then used this solution to later build a color PAL decoder. I like to tell stories like this in the hopes that I would inspire other people to deep dive into signals like this. And maybe, since I'm not very versed in GNU radio, maybe someone gets inspired to build a GNU radio solution. There will be some implementation details. I'm not getting mathematical, but I will get somewhat technical in this talk. My name is Oona. I work as a C++ programmer, and sometimes I even engage in Perl witchery on the side. And on my free time, I like to do anything related to DSP or signals. So I spend a lot of time listening, analyzing, researching. I like mysteries, especially. Anything can be a mystery. Any sound that I hear or radio signals that I receive. And I write about these mysteries in my blog. And this is my face. Hi, I'm awkward. Some background for this talk. About a year ago, I was listening to PMR 446 a lot, which is a European UHF band for walkie-talkies. I used my AirSpy R2, which has been my favorite receiver for quite some time. And in one place, I kept noticing this weird wideband interference signal on top of the band. It was very wide and it was very obnoxious. It completely blocked all the PMR channels. So I really had to find out the source of the signal because it hindered my fun activities. I had to find out if it's something that originates in my setup or if it's something in the vicinity so that I couldn't use that particular very nice QTH anymore. This is what the interference signal looks like in GQRX. This is just a small part of it. It spans a lot more frequencies. So it consists of very narrow and strong peaks that are all over the band. I listened to the signal by treating it as AM, and it sounded like video. Now, I'll explain what I mean. When I was a child, I used to play the 8-bit NES a lot, and the NES has a video output and an audio output, but the outputs are using a similar kind of plug. So it's very easy to mistake the video output for the audio output. So I would often accidentally plug the audio core to the video socket and hear the video signal, the vertical synchronization buzzing, which is 50 Hz here in Europe. And this interference signal sounded a lot like the NES video signal. Let's hear it. But why would there be a video signal, such a strong video signal, and such a wideband one here? That was a mystery to me. I had some suspicions, but I had to test this out. So I went through a lot of monitor display modes, so just common display modes, and tried to get the timings right so that I would get some kind of a picture. I could see if the signal makes sense as a video signal. So what I would do, I would take each sample from the radio at 10 megasamples per second, and I would take the amplitude of the IQ sample and just simply use it as the brightness of a pixel in an image. And then I would position the pixels so that it would be synchronized with that the vertical synchronization would always be at the same place. And this is what I got. The vertical synchronization signal is at the top, and on the left is something that appears to be a horizontal one, and the rest should be video, but it always seemed to be blank. But I noticed that the center frequency of the interference happened to be an integer multiple of the pixel clock of this display mode. So I kept trying the other multiples at other frequencies, and indeed I found some frequencies with video signals. I came home and I tested this with my own monitor at home. And here's my test setup. SDR SPY R2. I use a small whip antenna, or the telescopic antenna of the R2. I have the display very close to the radio, and I route this program that automatically synchronizes the image and displays the brightnesses and averages adjacent frames. And I get a pretty nice picture. So it's some kind of an emanation from the display or the cable or something. I tested this from the other room with a bigger antenna, which is the 9-element Yagi that I use for my PMR activities, listening activities. And when we get the frequency right and the frame rate just right, we are indeed able to synchronize it. The image is slightly more noisy, but especially if we average some more, we can get a pretty nice picture. So this became my remote HDMI viewer. Now, as I said, the center frequency of the signal emanated by the HDMI display is integer multiple of the pixel clock. But HDMI should be digital, so why on earth would it be transmitting analog video? Well, it turns out that HDMI transmits color values as 10-bit code words, and each code word, this is my speculation, each code word produces a very specific amplitude in the emanation, and it's very predictable in the way that the 10-bit pattern stays the same from frame to frame. And because monitor video tends to be very static, it's very easy to average between frames or integrate. Now, it's not possible to get a perfect copy of the digital picture on the computer display this way. For one, the sampling rate of the radio is only 10 megasamples per second, which is not quite enough to get everything that's going on the display. It's not a raw signal we are hearing, it's rather just an artifact. And there appears to be an echo from all the sharp edges in the image, some kind of a wavy pattern. I'm not sure what it is, but I think it's some sort of a reverberation in the cable, maybe. Could be. And also there's no way to receive color information from the display. As far as I know, the color signal in HDMI is spatially separated in the cable, so there's no way of knowing which color channel emanated which part of the signal. It's just one big lump of amplitudes. This picture demonstrates some of the shortcomings of this eavesdropping method. On the top is a raw signal that I sent to the display, and on the bottom is what I received on the radio. So here we can see that the sharp edges produce this kind of a weird wavy pattern. And we can also see the wavy pattern on the left, that's resulting from the horizontal synchronization signal, which is very strong. And this effect completely blurs most texts, for example. And we can also see that the individual grayscale values map to very random amplitudes. So photos and video will look very distorted because there is no linear mapping from grayscale value to amplitude. And we also see that color is probably not possible because the red and blue gradients seem to produce a very similar kind of pattern. Here I try to average the echo effect from adjacent scan lines, actually all the scan lines in one image, and then use this signal as deconvolution kernel to remove the echo, but the results were not very good. It was very noisy, and also it was very expensive for the CPU. Now this effect is nothing new. Wim van Eck already in 1985 wrote a paper about it, and that's why this kind of thing is often known as Van Eck freaking. He wrote about CRT displays especially, but in 2004, Markus Kuhn wrote about a similar attack against flat panel displays. And in his article, Kuhn suggests some mitigations. I think he mentioned LSB noise, or adding a sort of randomness to the least significant bit of the video so that it breaks the mapping of grayscale value to amplitude, and so it cannot be reconstructed at the radio receiver. Or you could also use smaller fonts so that it blurs them out more easily. And I'm not sure about this, but depending on how the signal is emanated, maybe some sort of insulation could work, or using shorter cables to minimize the antenna effect, but I'm not sure. I'm not sure how it's actually emanated from the display. This sort of thing is not a problem in HDMI 2 or DisplayPort protocols because those are either scrambled or encrypted, so there is no... So the pixels from frame to frame have no correlation. So how does it all relate to PAL video? Well, later, when all this was done, I wanted to record video from my NES console on the MacBook. But it turned out to be more difficult than I expected. I ordered like a cheap video capture device from eBay, but it took a long time to arrive, and then when it finally arrived, it turned out that the Mac software would only support NTSC. So the color, there's no color at all. And I tried filming the CRT display with the camera and even the flat panel display with the camera, but the results were not very good. So then I thought, I have this remote HDMI capture code. Could I use it to decode the video signal from the NES? Because the NES has a radio frequency output that the AirSpy R2 could well receive. It's at the 55 megahertz frequency. So for reference, here is a PAL signal. This is one scan line in an image. So we have a horizontal synchronization signal, just like in our HDMI capture. And then we have something called a color burst and a high frequency video signal, which takes most of the scan line. A PAL video is normally interlaced, which means that not every scan line is sent in every frame. But luckily, I don't have to take this into account because the video from the NES is progressive scan. Color in PAL is a bit peculiar. It's encoded in a subcarrier, and there are some phase shifts from line to line and all that kind of stuff, but I was willing to try. And I was quite quickly able to adapt this HDMI code to play Super Mario using my MacBook as a display for the NES. And the delays are actually pretty short from the radio to the display, so that it's a bit cumbersome, but I can actually play it. But it's still in black and white, so we need to take a look at PAL color. Here we see the video carrier from the NES. It's an AM carrier, and it just fits in the 10 megahertz bandwidth of the AirSpy R2. Now the chroma signal, which is the color signal, is on a subcarrier at around 4.5 megahertz. But on the LSB side, you can see something nasty going on. It's the audio signal, which is very close to the video signal. That is an FM carrier right next to the video signal, but it has been aliased on top of the video signal because the filter is not sharp enough, and it's way too close and way too strong for the filters. So I was kind of worried that the chroma signal would be completely destroyed by this, and there is really no way to avoid this. So I had to use a notch filter, a very narrow notch filter, to filter out just that frequency. Now the audio is FM, so it's very difficult to completely remove it when there is modulation, but at least I could get the middle frequency out. Here's one of the first color decoding results. I simplified it quite a bit. For example, I didn't use a COM filter, which is sometimes recommended for the PAL chroma signal. I used a simple bandpass fur filter, which is pretty CPU intensive. And I also couldn't get the alternating phase right, so my solution after this image was to simply ignore the color information from every other line and just copy it over from the previous line. And actually it's pretty unnoticeable, especially in a moving image. In this image, there's still some bugs. For example, there's no green color at all, but this was only a minor bug in my code, and I was eventually able to get a nice color picture Here's just a comparison of the Tetris title screen before the notch filter and after the notch filter. So the notch filter is able to remove quite a lot of the noise, and also it improves the synchronization of the color carrier, I think. Yes, a short demo of the decoding the PAL code in NES Tetris. So it's running on a 2013 MacBook Pro in real time at 50 FPS. The resolution is 240p, which is the native resolution of the NES. Okay, now we can move on. Here's a schematic diagram of the receiver that I wrote. So on the left, it's the AirSpy inputs and the notch filter. It's the very first thing that happens even before the amplitude demodulation, which follows. And then we invert the result of the amplitude modulation from unity, because broadcast video signals are sort of inverse AM to save power on the transmitter. Then we just copy the whole signal directly on the grayscale channel without any sort of filtering. I think it's good enough. It generates some noise maybe, which could be filtered out, but this is just a performance thing. And we synchronize the scan lines to a 15 kHz clock. And then the center part is the color decoding. So we use simple bandpass FIR to get the chroma signal. And then we synchronize a 4 MHz, 4.43 MHz carrier to the chroma signal. And we do an arbitrary phase shift because I didn't get it right. I had to sort of estimate the number of degrees to rotate the chroma. So it's a bit like an old TV where you used to have the hue wheel that you could manually adjust. Some profiling. Here we see that most of the CPU cycles are used in the audio notch FIR. So that is quite expensive. I'm using, I think it's 1000 coefficient filter. So it might be a bit overkill. And another FIR filter in the chroma decoding circuit is responsible for 12% of the cycles. I'm using SDL textures to draw the image, which is kind of efficient. Yeah, some performance considerations. The computer should be able to demodulate the image at 50 or 60 FPS. And there can be no missed samples, so it has to be kind of a real-time system. Because when you miss samples in the video signal and you don't know how many samples you missed, you lose synchronization and it looks very nasty in analog video. I exploited multi-threading pretty much. So all the pre-filtering is in its own thread, and the AM demodulation is in its own thread, and the UI is in one thread, and so on. And as I said, SDL textures is what I used to draw the image. And I used Liquid DSP, the library for this. But I see no reason why this couldn't be implemented in other libraries like GNU Radio. Something that I wish my program had, it should be even more efficient, because my laptop is old and I want to do other things with it, and I don't want it to get very hot when it's running. I want to use a radio with a slightly wider bandwidth. Now I know that the AirSpy should be capable of doing wider bands, maybe with a custom firmware, but I haven't tried that. I could maybe try with PAC-RF or something like that, so that I could accommodate the audio carrier and maybe filter it out properly. I'd like to rewrite the color demodulation code so that it uses something more clever and maybe uses all the scan lines for the color. And I would like to have this code support interlaced video so that I could, for example, watch VHS tapes. So thank you. I hope you enjoyed and found this interesting.